Right? Okay, so in this later section, we're going to cover all the things we learned in the previous week. So those things include the Schrödinger equation, particle theory, and which is part of the chapter 4, so postulate number 1. So first thing I want to talk a little bit about Schrödinger equation. So why we hear this phrase frequently in quantum mechanics, why this is important. Okay. So Schrödinger equation, when we talk about importance, we will kind of address this problem is how can we describe the motion of a physical system, but in different situations. Okay. So in classical mechanics and in quantum mechanics, we use different set of theories to describe the motions. So how about in classical mechanics, we use what to describe the motion? In physics, you learn the Newton's law or whatever, those things, right? So the Newton's law or Newton's second law, to be specific, talks about acceleration, talks about the motion. But in quantum mechanics, we know Newton's law does not apply to that microscopic world. So instead, that's why we learn Schrödinger equation. We use Schrödinger equation to describe the motion. So here also illustrates the importance of the Schrödinger equation. That is, this equation is equally important as this equation. So if you learn well in your physics, you will appreciate this equation very much, and so for this equation. Okay? So when we're talking about microscopic world, let's go into a little bit. They are all about microscopic systems, right? Like one particle, one electron, several electrons, several photons, whatever atoms. And they are closely related to probabilities. So right now you may not quite understand this is why, but along the second part of this course, we will talk about a lot of real microscopic systems. And within them, you will see, we will talk a lot about probabilities of finding something at some point, at some certain time point. Okay? And when we talk about probabilities, this one is also closely related to a wave function. Okay, now when we talk about wave function, we introduce this concept. It's no longer called a function, it's now called a wave function. So a wave function describes the motion within the microscopic world, or describes about probability. Okay. And when we talk about wave function, we know Schrödinger equation exactly addresses this part. Right? Because one term in the Schrödinger equation is actually a wave function. Okay? So based on that, here shows you the structure or the thing of the structure of the Schrödinger equation. And we're specifically talking about time-independent Schrödinger equation in our course. Okay? We don't care about time-dependent when we talk about this. So the general form is, do you still remember how to read this? The Hamiltonian operator, what of wave function? Times, can you say times? Operates on, okay? Hamiltonian operator operates on wave function equals inert, or that should be total inert, times or multiply, whatever, wave function. Okay. This is quite a general form. Okay, you can use everywhere, but to be more specific, it's equivalent to this expression. So the Hamiltonian operator can express by two parts. Okay. And the first part we reviewed the last section is called the kinetic inert operator. And this part is the potential inert operator. Here, we'll talk about it here. So here, the first thing is this triangle, the inverse triangle here, stands for another operator called the Laplace operator. And in three-dimensional world, you should have three terms. They are all second-order partial derivatives. Okay, so in some textbook, they will plug in here. So to make this equation seem to really long and scary. But anyway, they can just be expressed by one symbol. Okay. So then we'll talk about each terms here. Okay, each terms. As I mentioned before, so the first one, hope you still remember, is called kinetic energy operator. Okay. And of course, the second one is the potential energy operator. In fact, potential energy operator should be recognized as I raise the hat. That's for operator. But as I mentioned last section, it just equals potential energy. So that's why in Schrödinger equation, we get rid of the hat and just use the potential energy square. Sorry, not square, just potential energy. Okay, this is the second term. And how about this term? So what? I mentioned it before. Just one slide ago. The wave function and so for this. Right, so they are wave functions. And now about this? The total energy. So the total energy includes both kinetic energy and the potential energy. Okay, because it contains two operators here. Okay? So here's the general structure of Schrödinger equation. And we will use this equation. Well, actually, we will apply this equation to many, many real microscopic systems and derive all of the conclusions in the second part of our class. Okay. So here just give you the brief overview of the Schrödinger equation. And it's basically time-independent Schrödinger equation. So we talk about time-independent, so there must be another one called time-dependent Schrödinger equation. Okay, but this one is not required for our class. So here I just give you a whole picture. So form a complete picture of this. So it's left-hand side are the same. So the only difference thing is the right-hand side we changed. And here includes one term related to the time. Because here contains time, now the equation is time-dependent. So that's why we put time-dependent Schrödinger equation. So for anything or any function that talks about time, it actually talks about the motion. So that's why I mentioned, like, Schrödinger equation can describe the motion in a microscopic system and specifically a time-dependent one. Okay, to talk about motion. So if you draw this equation, it's like something moving, we call the wave path moving in a certain direction. Okay, those are some advanced quantum mechanics, and we don't need to care about this part in this course. But anyway, if you are interested in that, well, I can give you some more information about this part. Okay. So far, any questions about time-independent Schrödinger equation? Those structures, the meaning, all that. Okay. So hopefully now you understand why we need to talk about Schrödinger equation. Why Schrödinger equation is so important. Okay. If not question, let's go into a really big part in the last week. It's called particle in a box theory. This is actually the first real microscopic system we apply our Schrödinger equation to. This is the first example. So when we talk about particle in a box, the first thing is I want you to be clear about the picture of particle in a box. So why is particle in a box? So here I show you a box. Okay, something like that. If we only talk about one dimension, that's like flat, it's like a linear as the box. Okay. But this box is not an arbitrary box. It has some requirement about potential energy. So here I will show you the potential energy distribution. The first thing is we need to set up the coordinate in order to describe with using mathematical language. The first thing is we choose this one. So you can choose everywhere actually, but we choose this one will make our life easier. Okay, we choose this one as the original point, and we set this direction as the positive direction of the x-axis, and this direction will be the y-axis. Okay. And the length of the box is defined as a. However, sometimes it can be a real number like 1, 2, 3, 4. Okay, but here in general we choose a. A is a real number. It's just a constant. Okay. And we know that for the potential force outside of the box, if we define this as the box, so if outside of the box, then infinity. Okay, so sometimes we call particle in a box, like the box has infinite high walls. The infinite height, there are 2 walls here. And how about within the box? You still remember what is the potential energy? 0. Great. So when we say potential energy is 0, we sometimes call it free motion or free particle. So next time when you see free particle in the question, that simply means V equals 0. You can freely move it without any potential effects from others. Okay? So this is actually the picture. As I mentioned, since I set up the coordinate, I can use the mathematical language, and it's like this. Okay, so potential is a function of the x of force. So when outside of the box, potential is infinite large, but within the box, just 0. So that's the picture for the box. Okay. And then we will put our electron in, or whatever particle into this box, and that will form the particle in a box. So that's a picture of it. But before talking about that, another important thing is boundary conditions. If you still remember, what are the boundary conditions for particle in a box theory? You have actually one question in your homework. The function, the wave function should be what?
0 at the boundaries.
So remember that? The wave function should be 0 at 2 boundaries. Why? Okay. Because think about that. If you put a particle here, outside of the box, the potential energy of that particle is what? Infinitely large, which does not make sense. Now how can your energy be infinitely large? You're quite stable actually. So you're quite unstable. So since the particle cannot free here, so simply means the probability of finding particles within this 2 shaded region is 0. Okay, so because, also we will mention that later, so the wave function is continuous. That simply requires when wave function reaches the boundary, it must go down to 0 in order to be continuous with this part. Anyway, so if you don't understand that picture, that's okay, but I want you to remember is, quite easy thing is, if we ask you what are the boundary conditions for particle in a box theory, it simply means the wave function must be 0 at 2 boundaries.
So for the whole particle in box situation, you're trying to find 2 main things: the energy of the particle and the probability that it's in any certain area.
And the wave function of that particle. So 2 things, as you mentioned, 2 things. One is energy. The second thing is wave function.
Wave function.
From wave function, we can evaluate probability. We can evaluate, some, as you mentioned, you talk about like probability. We'll talk about it later.
Okay. And that's the Schrödinger equation.
That's a Schrödinger. All of that from the Schrödinger equation. Okay.
So is that the energy of the box or the particle?
The energy of the particle.
Part of the particle.
I will talk about that later. You've heard about that. This is just a starting bit. So before we talk about energy, before we talk about wave function, I want you to be clear about the boundary condition, about what does the box look like. Okay, those are crucial things for understanding particle in the box. Okay? So any questions about the general picture and boundary conditions? Great, we understand it. So then we talk about energy. Let's talk about energy. So here, energy is the energy of the particle. Okay. If we want to talk about one dimension, then again, we started from Schrödinger equation. This is a general form. And we can somewhat solve it. And we showed the derivation in class, so I will not spend time here. And also all the derivations are on your textbook. And we can get this equation. So here talks about the absolute energy of each integer level. It's something like the Bohr's model. We talk about Bohr model. We talk about absolute energy of each orbitals, right? So here is absolute energy for each energy level. Okay, and here with a subscript n simply means the quantum number. So the energy is actually dependent on the quantum number, and the dependency is n squared. Okay, so E equals this one. And the whole part actually, if you have a 1 electron, the mass is fixed. The length is also given to you, and actually a constant. So the remaining part are all constant. The only thing is n squared. We can say the energy is directly proportional to n squared. Okay, and based on that, actually, we can also evaluate the energy difference between 2 energy levels. Okay, again, like n final square minus n initial square, somewhat like the Bohr model. Okay, and based on the 2 equations, actually, you can evaluate the energy of each different energy levels. So let's say we can plug in n equals 1, and we get one number, right? And we can plug in n equals 2, we'll get another number. N equals 3, n equals 4. You can just plug in. And you can actually draw it on your paper, and you'll get some picture like that. So let's say the E1 is about this high, and the E2 is about this high, the 3 is this high, and 4 is 5. And naturally, you will figure out actually the gap between the first one is smaller than the second one, is smaller than the third one, this one is smaller than the fourth one. Okay, and naturally you get that picture. So actually this energy level, this energy gap is different from Bohr model. Right? In Bohr model, the energy gap becomes what? Smaller and smaller when the quantum number increases. But here it's getting bigger and bigger. Okay. This is because of the independence, or the dependence n squared. So I will show you in math actually. I'll show you this time. So in the following sections or whatever courses parts, when we talk about energy gap, we can always use this kind of method to think. So if we draw the x here, and this is the y is defined as En. So actually it's not n, x. So let's set to the x to be n. So the y should be the En. En is like this. So actually give you a picture like that because of n squared, right? So let's choose n equals 1 first. So how can we read the value for En? If we based on this picture. When you remember in math, how can we read it? We read it. Well, we can solve it one thing, but we can just read it from here. Right? And so the first one, of course, give you 1. I mean, the unit, okay? I just get rid of this constant. It should be 1 times the constant. How about 2? 4. 3. 9. 4. 16. Okay. That's like this picture. And then where's the energy gap between two adjacent energy levels? This one, this one, this one. Can you evaluate it? 3, 5, 7. That's by increasing. Okay, naturally you get this picture. Okay, everybody clear about that? So in polynomial box, the energy level gets larger and larger when quantum number increases. So here I ask you one question. What's the n number for the lowest energy level? What's the quantum number for the lowest energy level? Everybody agree that it's 1? Well, I bet you think n is 0 because when you plug in n equals 0, it's actually smaller than n equals 1, right? Exactly, you cannot. So be careful, n cannot be 0. Okay, n cannot be 0. So the first starting n will be 1. So that also means the lowest energy will be the energy with n equals 1. So actually you see the first one, the lowest energy is not 0. There's some finite value there. So in the following chapter we will call this energy, this one amount of energy as the 0 energy. So 0 energy does not mean 0. Okay, 0 energy means something, it's finite value. Okay. So here is one you be caution about that. So we talk about one dimension quantized energy. Okay, energy is quantized. How about n dimensions? Can we just generalize it? Well, it's pretty easy for you to generalize it. It's by doing this way. So you simply add all the energies from different dimensions together. So you have 3 dimensions. Then if you figure out the energy expression for each dimension, then you simply add them together. Okay? Give you one example, like 3 dimensions. Well, if we don't look at the whole, if we only look at this part, it actually describes the energy for the x dimension. Right? This part will give you the energy for y dimension. This one will give you the z dimension. So you have different directions, x, y, z. But when we talk about the total energy for this 3-dimensional, or for this particle in the 3-dimensional box, we just add them together. Okay, I'll give you this. Okay, clear about that? So in one of your questions, one of your homework programs asks you to write the energy expression for a particle in a 2-dimensional box. So in a 2-dimensional box, then you just figure out each energy expression in one dimension, and then you add the 2 together. Okay, so simply you add all energy terms all together, and it gives you the total energy expression. Okay, one special case is when A equals B equals C. We call this cubic box. Okay, we talk about a cube, A equals B equals C. And then we can simplify this equation as this expression here. Okay, it's just a math, right? But you convert A, B, C to A, and then the only different thing is those quantum numbers. Okay? Clear about that? Okay, so so based on this expression, actually, we can talk about another important concept, that is degeneration. Okay, so first let me ask you, what is degeneration?
Multiple energy levels have the same energy efficiency.
Exactly. How about others? What is degeneration? So at least you need to have that one keyword that is identical something. Okay. So degeneration talks about several energy levels or several states. If we generalize it, several states have the identical eigenvalue. Or to be specific for this situation, that would be the several energy levels have the same energy. Okay, so the difference is with the same thing, with the same eigenvalue together, that means they are degenerated. And the number of those states, or their states, equals degeneracy. And in quantum mechanics, we put a small letter g to represent that. So if we say g equals 4, simply means within that eigenvalue, we have 4 different states, but all end up with the same eigenvalue there. Okay? So while we talk about that, actually we can give you some questions like, so actually you can check your figure there in your textbook. Okay. So we can actually give you some programs or questions in the exam or whatever quiz to ask you to compare the different energy levels. So which one has a higher energy, which one has a lower energy. Okay. So let's assume we have a total energy expression for particle in the white box based on this expression. It's going to be particle in the white box. Give me some adjectives to describe the box. It's cubic, or it's better to, it's more accurate to say 3-dimensional cubic box. Can everybody figure out? By looking at this expression, you can actually say this is a particle in a 3-dimensional cubic box. Okay, so once you know that, so please compare. There are 3 sets. 1, 2, 3. Please compare the energy. Which one is higher? Which one is lower? Okay, for the first one.
So can you have an n equals 0 there?
Well, is this larger? Is this one larger, equal, or smaller?
Smaller than what?
Smaller than this one, right? This one is smaller than this one. But how could you tell? How could you tell which one is higher, which one is lower?
Add up the numbers.
You plug in the number in, right?
Yeah.
Plug in the number. So if you plug in the number, the first one will give you 2. So 1 squared plus 1 squared plus 0 squared equals 2. This one will give you 5. So this one will be higher, right? Everybody agree? Everybody agree? Except you, right?
Can you have n equals 0?
Exactly, this is invalid. Because of what I mentioned.
Wouldn't it just be a 2D box instead of a
But they're
3D
using
box?
separate zeros.
No,
every
it's-
single line.
Quantum number can never be 0. Okay, if you say quantum number is 0, it's not nothing like a two-dimensional flow. They're not in the same system. Right? Even in 2 different boxes, if you say 2-dimensional boxes, well, they cannot compare. Anyway, we say this question is invalid. So if you see this happen in your quiz or whatever example questions, let us know immediately. Must be some problem with that. Okay, then how about the second one?
Three equals
14? Or what?
14
the same.
They're the same.
They're the same. How could you tell they're the same?
You got the same numbers.
It's a trick, okay. Anyway, if you don't know, the absolute value, whatever, you plug in n. Okay, nx equals 2, ny equals 1, nz equals 3. Well, by the way, how could you know this is nx, this is ny, this is nz? By the definition here, nx, ny, nz. So here, nx, ny, nz. Okay? So you plug in 3 numbers here, you plug in the 3 numbers here, you will figure out actually this part for the 2 energy levels are the same. So then we call this 2 energy levels what? One word. Degeneration. So something, I remember in gym camp, there's a popular question type like fill in the blank, right? But in our course, we'll not do that. But anyway, this is a really good practice for it. Okay? So because the two energy levels are the same, so we call the two quantum states, actually, this quantum state and this quantum state, they degenerate with respect to energy. Okay, then how about the third one?
They're not degenerating.
They're not degenerating. So which one is higher, which one is lower?
The second one's higher.
Okay, again, right, you can calculate the two, right? Evaluate the two, the square it out together. That's one give you 21, that's one give you 22, so this one is smaller than this one. Okay. Any question? So I can just change the question a little bit to make another new question. Is I can just give you this and ask you to list all the degenerated levels for us. Okay, ask you to list the whole. So after this one will be one answer, right? But sure, you should have more. So this could be another question type for this part. Okay, anyway, any questions about degeneration here and also the degeneracy? And how can we compare, how can we tell if they're degeneration or not?
So with the degenerate, they do have separate different wave functions.
Yes.
Okay,
But they'll end up with the same eigenvalue.
right.
Yes. Okay, so no more question. Let's talk about wave function. As I mentioned, for each microscopic system, when we talk about quantum mechanics in this class, we care about two things. One is the total energy, like just talked about before. Another one is the wave function. And from wave function, we can evaluate a lot of valuable things, which we'll talk about in chapter 4. Okay. So anyway, let's back to particle in the box wave function. Again, by solving Schrödinger equation, let's keep it apart. By solving Schrödinger equation, you can get the wave function exactly this. Again, also quantized because it depends on the n, and n is integers. Okay. So n can be 1, 2, 3, and again, n cannot be 0. Okay, once you can try plugging n equals 0, the sign function is 0. So no wave function, no particle. You're talking about empty box. Okay? But here we want to talk particle in the box, so there must be a particle. So n again cannot be 0. So if we draw the picture by plugging different n number, okay, n equals 1, n equals 2, n equals 3, 4, 5, and more, and also satisfy the boundary conditions where the wave function at two boundaries must be 0. Like this. You'll get this picture. Okay, it's n equals 1, n equals 2, n equals 3, naturally by the mass. And then we define a very important concept is called node. So a node simply defined as wave function is 0, but not including two boundaries. And on two boundaries, wave function must be 0. But except the two boundaries, if we can still find more points where the wave function is 0, then we define that as a node. Okay, so based on this definition, can you tell me how many nodes for n equals 1 state?
0.
No nodes. How many nodes for n equals 2? 1. Do you know where is it? The middle. X equals A over 2. Great. How about this?
2.
1 and 1 here.
Are the nodes always at A over N? Separation between them, or no?
Depends on the wave function, how you write it. If I write like sine, it is. But if I do a different one, yeah, we would.
So cosine it wouldn't be at A.
Cosine will still be the same.
Oh, so we can go.
You can go after a different wave function plug in, might give you different pictures.
Okay.
But sometimes the symmetry is quite beautiful. Okay. And some symmetric things usually, in general, works for the real system.
And this is just sort of normalized.
Normalized. Why is normalized? We have normalized the coefficient here. If it's not normalized, it just affects the intensity. It will not affect anyway. Will not affect the points here.
Oh.
The points, the position are always there. The only thing is this one will be higher. Like this. Okay, that's if we don't normalize it. But anyway, we'll normalize it first. We'll talk about normalization later. So based on that, can you give me can you just conclude one relationship between the number of nodes and the quantum number? What is -1?
Number of nodes.
Number of nodes minus 1. Let's say this way. A quantum number n corresponds to the wave function have n minus 1 nodes. Okay, so nodes number always have 1 less than a quantum number.
And that's regardless of the sine, cosine, tangent.
Regardless.
Okay.
Regardless of that. Okay. Alright. So let's see the wave function. As we'll also discuss in class, we can actually product a complex conjugate of the wave function. Okay. So you times the star with something star with this complex conjugate of this wave function. And we can also write it this way. So pay attention, here is not square. It's not just a square. It's square plus 2 lines here. Okay, here the line means the magnitude. Okay, anyway, if you want to write square, make sure you have 2 lines. But if you don't want to write square, you write this. Okay, either works. So simply, because this wave function, as I showed before, they're real functions without any imaginary numbers. So based on that, we can just simply square it. Once you square it, you get this. And then we define this one as probability density. Okay, anyway, we'll talk about that in chapter 4, the postulate number 1, formally. But here, just give you the expression. So if you product the wave function with its complex conjugate, that will give you the probability density. So simply means if I square the previous wave function, I will give you this picture. But pay attention, all the 0 points or all the nodes, they are still there, they are fixed. It's not affected by whether you choose the probability density or not. Okay, but based on that, I want you to also tell me how many maximum points in each probability density distribution curve. Okay. By the way, this curve, those curves, we call it the probability density distribution curve. It simply tells you the probability. Okay. So here, this one means the probability will be the highest, while here the probability will be 0. It's simply the value of this curve, reading from the y-axis here, will give you the probability density. Okay. But based on that, can you tell me how many maximum probability density can we find in n equals 1? 1. Where is that? A over 2. Okay. 1 maximum. How about 2? 2 maximum. How about 3? So what's the relationship between the maximum points with quantum number? They're the same. Okay, they're the same. So you may wonder like why I talk about this. Okay. That's because we can have these questions. Please determine the n values for the wave function of an electron in a particle box, and I will give you a lot of examples. So the first case is, what's the n value for the state which contains 5 nodes? 6. So what's the n value? What's the n with the number of nodes? If n equals 1, no node. If n equals 2, 1 node. So it's actually n minus 1. So here we have 5 nodes. Simply means n equals 6. Okay. Second one, the state which contains 10 points, where the value of wave function is 0. What's the n number for that? Well, by the way, why we need to know n? Because once we know the n, we can actually write out or express the energy and also express the wave function, because it only depends on n. Right? Only the n is an unknown number. So 8, 10.
So does that count boundaries?
Very good point. Do we need to count boundaries?
Yes.
Yes, right? I say wave function equals 0. It of course includes 2 boundaries.
7.
So actually, how many nodes there?
8.
8 nodes. If 8 nodes, what's the n number?
7.
9. Okay. Kind of tricky, huh? Alright. Third one, the state where maximum probability to find the electron lies at the middle of the box.
N equals 1.
N equals 1. maybe it's back to the picture. A equals 1. Just one thing.
But doesn't that also lie?
But we can find some maximum probability at the middle. And of course, A equals 5, A equals 7. They're all odd numbers. Okay, all the odd numbers. Okay, all the odd numbers for this. The ground state. What's the definition of ground state? With the lowest energy. Okay, so A equals what? A equals what? 1. Okay, can you see A equals 0? Invalid. The fourth excited state. What's the definition for excited state? Above ground state. So the first one above ground state will be the first. 10 equals 10. Okay. The first excited state will be A equals 2. The second will be A equals 3. So the fourth will be 5. Another problem, which is the real question from 3 years ago from midterm. Question 5. I will not ask you to just solve that question, but the only thing is, can you tell me what's the quantum number for this transition? So the fourth smallest observed frequency for a transition, so please tell me, because we're talking about transition, it involves 2 quantum numbers. Can you tell me it's from which quantum number to which one? Well, in a real exam, you don't have this picture for you to help you think. Okay, here I just reduce the difficulty. The fourth smallest transition, smallest observed frequency.
4 to 1.
Yeah.
Or either 5.
I mean, I don't know.
It's either 5 to 3 or 4 to 1. Because 4 to 1 is the fourth, or the
Yeah.
third
Well,
smallest.
5 to 4 would be smaller than 5 to 3. But
Think about that. If you are talking about small, of course you cannot get 2 energy levels, right? Once you get 2, if you're across 2 energy levels, it must be larger than across just 1 energy level. So there must be some from adjacent to energy levels.
Between 4 and 5.
yeah, 5 and 4.
5 to 4. Everybody figure out? Okay, the first thing is we talk about small. So must be the transition between 2 adjacent energy levels. But anyway, before that, you can actually translate a little bit. Let's say the fourth smallest frequency. If we have a small frequency, that means the energy is what? Is high or low? If small frequency, that means energy is, well, very high equals frequency. So if frequency is small, energy is also small. So the fourth smallest observed frequency must be the fourth smallest energy transition or energy difference. Okay. So of course, well, can you see this one in the first one? No. And it cannot be 0, so you cannot jump back to 0. Okay. So this will be the first, the smallest energy level. I mean the energy gap. Second, the smallest energy gap. Third energy gap. Third smallest energy gap. Fourth smallest energy gap. So the fourth smallest observed frequency will do this. Okay? Once you figure out actually Ni equals 5, Nf equals 4, you can plug in the expression for delta E and you solve for A. That's the answer of the box. Okay, so this is the only tricky point here. Can you figure out the correct quantum numbers? Okay. I just leave this question for you. You can solve the thing. The key point is to figure out the transition. Okay, any questions? Okay. If not,
Just theoretically solving that equation. So you plug it into that equation.
not this one.
The En equals NH.
Remember that?
A squared over 8ma
Square or not?
ma squared, yeah.
Square.
No, it's a squared. A squared.
Oh, right. And New and
Well, yeah, but eventually, but how do you switch between the energy and the frequency? Because you're only given the frequency.
Oh, really?
Is that okay.
Okay. So what happens when n approaches infinity? Okay, let's think about that. When n approaches infinity, what's the number of nodes? Also infinity nodes. Well, infinity minus 1 also infinity. Okay. So there are infinity nodes here. So say when n approaches infinity, so think about that. We have if I have this one, it will be this much nodes here, right? But now the situation is that the nodes number are infinity.
0.
So it's something like that, right? I'm not draw it. But it's really closely packed together. So you squeeze this wave function to infinity, you squeeze it. So then I will give you a picture of like that consecutive. So now all the wave function is actually one line. It depends on the intensity. If you change the intensity, this height will change. But anyway, that's not one line. So this is like what? Let's say if once you square it, you convert to probability density, that simply means the probability for you to find that particle within the box is even everywhere. Everywhere you have equal chance to find the particle. That's exactly the classical features. So think about that. I have a box, and I put a particle into it, and ask you to find the particle. So in a classical picture, when you open the box, assuming the particle is still moving inside, okay? So when you open the book, it's actually for everywhere, the chance to find that particle should be the same, like evenly distributed. Okay? So the probability becomes even everywhere, recovers the classical pictures. So that's actually the bridge between quantum mechanics and classical pictures. Okay? They're connected by the n value. So if n is small, it's quantum picture. If n is large, it goes to infinity, it's actually classical pictures. Okay? So we talk about the wave function in one dimensional. So how about the wave function in n dimensional? How can we generalize it? Well, I hope you still remember, how can I generalize the energy levels for n dimensional?
Just add the other dimension.
Add them together, right? So for wave function, you times them together. Okay, simply times them together. So give you one example. For three-dimensional wave function, the only thing you to do is to figure out the wave function for each dimension. Let's say for the x dimension will be normalized. So this will be the wave function for x dimension, the first dimension. And we know the second one will be okay. And the third one is so let's assume you successfully figure out the nx, the n1, the nc. Now the three wave functions you all know. But I asked you to express the total wave function for this particle in a three-dimensional box. Just times them together, and that's all. Okay. Once you times the three together, you combine the coefficients, so it's not A, B, C, A. You combine them together to give you this expression. Okay, again, question 4 in homework talks about something like that. And again, we have a special case where A equals B equals C in a cubic box. So we can simplify this expression as this. And we get A cubed, and average A, B, C can all become A. Okay? Any question? So if you want to express the total energy for different dimensions, you add them together. If you want to express the wave function of the n dimensions, you product them together. That's the trick. Okay, no more questions. So Let's talk about the application of particle in a box theory. Okay. So why particle in a box theory is important? Why we need to learn it? We learn it because sometimes we can explain some quantum phenomena. The first thing is the color of quantum dots. So I usually, not usually, I also mentioned this in the first section, right? We put a question mark here. Why we have different colors here? So here we'll come back and solve that question mark. But the thing is, we have quantum dots that just each dots. By changing the size of the quantum dots, but keep the composition the same, we will be able to see different colors under UV light. So here I talk about UV light, okay, about those emission lights. So here is, well, how can we expand the different colors? The thing is, we can imagine we have quantum dots like that. And because quantum dots are usually here, it's actually CDSE, the Km selenide. And I just one semiconductor. And when I just tell you, once you shine the light on it, it will create electrons. Sometimes we call photoelectrons. And not eject from the surface, but just create it within the semiconductor. Okay. So these electrons, they can move within the particle, but cannot jump out because of the work function or whatever the potential energy that refine it. So based on this picture, we can make an approximation for this model is electrons is confined. So this electron is confined within the quantum dots in a one-dimensional particle. Okay, so this, you can imagine the quantum dots is as a box, and the particle is the electrons that is moving inside. Okay, so this is the approximation anyway. It's not quite accurate, but it's approximation here. So we call this an electron in a round box or whatever, a spherical box. So we can also derive the energy for the transition. So here's the transition system. So once we have this two, we call it the energy band. Anyway, there's lots of concept which we can talk about in the advanced PChem lab. But here, let's imagine there are two energy levels here. And this is the ground level, this is the first excited energy level. So once we shine the light, the electrons will be promoted to the first excited state. And because the excited states, the electron there have a higher energy, it's not stable, so it will jump back. So by jumping back, it emits the light, okay, and it emits the energy. So how can we calculate delta E here? If we use the conclusions we derive in particle in a box, that will be something like that. So only the thing is you change A to the radius of the particle. Well, again, just approximation. I know it's not quite accurate. But anyway, it involves two quantum numbers. But let's assume all the colors coming from the transition between the first excited state and the ground state, then the NF and NI is the same for different ones. But the only different thing is the radius or radii of those quantum dots. So then you can see that the delta E actually is inversely proportional to 1 over r squared. Simply means by changing the size of the quantum dots, you can change the delta E. And the delta E is actually the energy of the light. And the energy of the light is Hc over lambda, and lambda determines the color. So then you change the size, you change the delta E, you change the light, the energy of light, then you change the wavelength, then you change the color. And to be more specific, actually you can see if the radius is small, the delta E is large. Delta E is large means wavelength is small. Wavelength is small means the color shifted to purple. And you get this color. But if your particle is large, you get some yellow or whatever red. Okay? Any question about that? So we can actually expand the color. Okay. So let me make one advertisement. So this Friday, on this Friday, you know this museum in Santa Cruz will host a Glow Festival. And our lab, actually, I will perform a on-site live demonstration of quantum dots. So we'll show you different colors. So if you have time, you are welcome to go to that museum, and there are many other glow thing stuff there. But one of the stuff will be performed by our lab is doing the quantum dots. Okay, and you can see the real color difference. Okay, anyway, just tell you there's something happened this Friday about, I think it's starting from 7 p.m. Another application is tunneling effect. Tunneling effect. So let's just give you a brief idea. You don't need to really understand this. The thing is, when the potential wall is not infinite high, it is finite, with finite height there. So then something interesting will happen. That is, now the electrons cannot be confined within the box. It actually can leak through the wall and to outside. I mean, if the potential wall here is not infinite high, okay, if not. So then they'll leak. So it's something really strange. The electrons can go through the wall without destroying the wall. That's something weird happening in quantum mechanics. That's why I tell you, don't use your common sense to understand this picture. Okay, it leaks. So it's something like, for repeaters, in quantum mechanics, we must climb over the hill. That's us. But for electrons, you can just go directly through the hill to the outside. Okay. So why this is useful? We can use this effect to construct what's called the scanning microscopy. Okay. So it actually uses this effect to probe the surface structure of some substrates. And here it gives you the picture of the graphite. As we learned in gene chemistry, graphite is actually layer structure with this hexagonal pattern here, right? And actually shows you the pattern through this microscope. Okay, this depends on the tunneling effect, but also related to particle in the box. Okay, so any question about particle in the box? Okay, if not, we'll spend some time talking about postulate number 1. Okay, this is only number 1, but in the quantum box, we have several formal postulates of quantum mechanics. Simply means quantum mechanics are just built up based on those postulates. And there are 5, actually, we will talk in this class. But today, we're going to talk about this first one. Okay. We're going to talk about the first one. So the statistical meaning of wave function. So what is statistical meaning of wave function? It's actually related to the Boyle interpretation of wave function. So Boyle thought, or proposed that state function describes the microscopic state, and we put the function, the notation here. So actually sometimes you can say wave function. Wave function describes the microscopic state. This one at a certain point, at a certain time. And then define the probability density is the product between the complex conjugate of that wave function and the wave function itself. So we're already talking the particle box. So here I'll give you a formal description. So what is probability density? Probability density means within a certain space. So let's say we have a space like that. It's two-dimensional space. And we have a particle confined within the space. And they're moving along with the time. So at each time point when we open or when we observe the system, we will actually find the particle out of where with some probability. Right? So within the whole probability, if you divide the whole space into a finite infinitesimal volume, so that each probability falls into the one single or a small volume there is actually defined as probability density. So that's why we call dp over d tau. D tau is means one space point. Okay. So the probability of finding that particle within that small point is defined as probability density and can be calculated by doing this. Okay, this is the second thing. And the third thing based on that is probability of finding a particle at an infinitesimal volume d tau at time t is this one. Okay, so pretty naturally go from here to here because you just move the car here. But here it talks about the dp. So how can you calculate the infinitesimal probability? Is actually this. Okay? And this expression, the famous expression, is defined as the statistical meaning of wave function, or sometimes called a probabilistic interpretation of wave function. So it actually connects the wave function with probability. And that's why I talked at the beginning of the section, I say probabilities is closely related to wave function. How? By this equation. Okay? Any question? A little bit abstract, okay, a little bit. Then we talk about normalization. So there are several points for postulate 1. Okay. The first one is what I mentioned, Boyle interpretation of wave function. So what is wave function? Wave function is something related to probability. And then how can we calculate the probability? The first thing is we normalize it. The normalization. And the normalization, the probability of finding a particle within the whole space, within all space, must be 1, right? If let's say we confine the electron within that box, so we must know the electron must be within the box. So if we search every corner of the box, if we search all space of that box, we must find the electron. So simply means the probability of finding that electron within the whole space must be 1. Okay. Understand the picture? A little bit abstract. Okay. So that simply means that things can never happen because you cannot just find a half electron or a half human. Right? Within the space, we have a half one. So this is forbidden. So think about that. You search every corner. We know there's 1 electron. We know there's 1 human being within our classroom. And if we search every corner, we must find that data. We cannot just find 1 leg or 1 arm. Okay, so the probability must be 1. So then, if we express it, the searching corner were defined as the integral. So the first expression expresses the one in Cartesian coordinate. That means the traditional x, y, z. So if we say within a 3-dimensional box, the normalization is like that. So think about that. This part, okay, this part, exactly defined as dp, right? The probability of finding the particle within dx, dy, dz. Right now we're talking about all space, so we integral for all space. So this one must give you a number 1. Okay, this is called the meaning of the physical meaning of normalization. So this equation is reduced one. It's actually a simplified version if you use the spherical coordinate. So we will talk about in the following chapter. So you don't need to chair this time. So be careful about normalization. I know there will be a lot of questions asked you to normalize a function. The thing is, the above equation equals 1, here equals 1, only works for normalized wave function. Okay. So if you write this expression, just be careful. It's not always equals to 1. Only if the wave function is normalized can the result be 1. Okay. Otherwise what would happen? If your wave function you use to do the integral is not normalized, so you get some finite number, a squared. Right? A squared is still constant. You still get a constant. But anyway, the constant is not 1. Okay, so if you do an integral, this equation, and you get a non-1 value, simply indicates those wave functions you use are not normalized. So please normalize it. Okay. So then when we talk about normalization, how can we normalize a wave function? So we only need to follow those steps. Then it can work for everything, and for every wave function. Every question asks you to do normalization, you follow these steps, and you can work it out. Well, it depends on your math. So the first thing is, please put a constant before the function. Let's say a. Okay. Let's say the question asks you to please normalize the side here. Well, how can you normalize it? First, put a constant in the front of the wave function. Okay, so easy. Step 2, also very easy. Please write down this expression. Simply means you product its conjugated with itself and do the integral with respect to all space. You write it down. And the third step, please evaluate this integral. Okay, please evaluate it. Well, that depends on your math. If your math is rusty, sorry, you cannot get the number. But let's say if your math is okay, And actually you can get a squared. You get a finite number. But anyway, we'll talk about something else. So here I say complex conjugate. Okay, complex conjugate. So that's actually that only affect to one will affect the complement number. Okay, well, that means the number with imaginary part. Okay, so E, the number is C equals A plus BI. What is the complex conjugate for C? I'm not clear about the definition. You only need to change the sign of I. Okay, give you one another information. So let's say we have a wave function psi x equals into I h1 e to and A is a constant. So what is the complex conjugate of psi x? I h bar. Well, you just change I to negative I. Everywhere. Okay. That's it. And then you times this one with this one. Okay. Just be clear about that. Well, you solve the equation and you get A, right? You get A, then that's your normalization constant. Then you normalize the function. You get it? Okay? First step, put an A. Second step, write down the integral. Third step, evaluate the integral and you get A. Okay? Once you get A, plug it back. That's for normalize the function. Okay. So let me give you one example. So for example, I give you this equation, I ask you to normalize it. So this could be a one question in the exam sometimes because we tend to give you identity to make the calculation a little bit hard. But anyway, if you are clear about normalization, you just follow the steps. Then it's just the math. But you give the most of the partial credit for the correct expression for normalization. But let's say we don't need to care about this right now. Don't get scared by that one. How can we normalize fx?
Constant.
For a complex conjugate, product them together. So fx star. Right. And then what? Another integral. Oh, we have put a concept on this one. Ask you first to examine whether this is normalized or not. Let's just do it to see if we can get a one or not. Okay. Right? Doing the integral with respect to all space. What is all space? From 0 to infinity. But don't forget about the two bounds here, okay? If you correctly write down this expression, in most cases, you get half of the point of this question. And another half a point goes to mathematical calculation. Okay. So I'm mentioning here, the first one, we check the integration. We do it like this. If you write down this one, you get half of the point. And you plug in the wave function. And you do the math, whatever I do, not sure the math. And now you use identity. Provided to you. Okay. So that we can go back and check the calculation, and you will reach Q. So actually, you get a constant 1 over 4BQ. But we know this is not 1. So simply means this wave function is not normalized. Okay, it's not normalized. And let's define this number is A squared. Then how can we normalize the function? I mean, if we can just put A in the front of the wave function, that's something you need. So not normalize, and then normalize the function, but put 1 over A. It's not A here, it's not A. A little bit tricky here. If you put A squared here for this constant, when you normalize it, you not put A, but you put 1 over A. simply because once you normalize it, you see, if you put 1 over a squared. So here's 1 over a for this one, 1 over a for this one, 1 over a squared. When we down here, all the sets will give you a squared. So a squared over a squared, now you normalize it. Okay, now you normalize it. So then the normalized wave function will be like that. Okay, anyway, we don't have much time to just go over step by step, but anyway, let's start this math. Hopefully you spend some time going over the math. And also, you will see when we calculate some math, which is the integral here, we sometimes encounter the trigonometric functions. And I want you to be clear, just be familiar with some identities for those functions. Like, okay. So the first one equals what? 1. Second one, it's your cycle. It's your cycle. Third one, okay, cosine square minus sine square. Or you can use this one to another 2. Still remember this? Sine x squared. Okay, anyway, let's go back to check. Okay. Why do you know that? Right? Sometimes we ask you to evaluate this. Okay. Why do we do that? Think about that. Wave function for particle in the box contains sine term. Okay, when you calculate the probability using particle in the box wave function, you actually have the squared, you have sine squared. You have sine squared, that's exactly something like that. Well, you calculate the normalization constant or whatever, you calculate the probability, you will must be incompetent. But anyway, we don't have time to go over all the things. All the thing I want to tell you is you can convert the square term to something like that, and then you can do the following evaluation. Right? If you're using, you can go back and check this calculation. Okay. Another thing is we can normalize the function and we can also calculate the probability. So here I just compare the 2 different things. Okay. If let's say the first one is normalization, if we want to do the normalization, what is the integral region? The all space. Okay, all space. And also mathematical expression, we'll just go over in your mind. Like that. Okay. So the physical meaning is like normalization. Okay, similarly, we can do the probability calculation. Okay, to calculate probability, this time the integration region is not the whole space, but a certain region within the whole space, or the whole space. And this time the mathematical expression is a little bit different. The only different thing is the bounds here. So now the probability will have the bounds. So let's think about, let's ask you to calculate the probability of finding the particle between 0 and a over 2. So then 0 and a over 2. Other parts are the same as normalization. Okay, and then that's something you need to be very careful. If we calculate the probability, make sure your wave function is normalized. Okay, if you use a non-normalized wave function to do the calculation, you'll get something wrong number, or sometimes can be larger than 1. Okay, please use normalized wave function to do the calculation. So that's why for some questions, in order, when you do the calculation of probability, always keep in mind, always remind yourself, is this wave function normalized? Sometimes will be the trick there, okay? So that's the probability of finding the particle within that certain region. And another thing, the last thing is postulate 1, define a well-behaved function. So a well-behaved function should satisfy all the requirements. There are 3. Okay? So we have make it 3.5. The first one is should be continuous. Because of the Schrödinger equation, which involves all the differentials, and it must be differentiable. And we know in math, we define, or we say, if the function is differentiable, it's simply continuous. Okay. The second one is single value, in order to be a function. So, at the same position and at the same time, we cannot find a particle with 2 different probabilities. It must be 1 probability. Okay. The third requirement is finite everywhere. That also simply means, because the wave function here, a function, it represents the probability. So we cannot get an infinite probability of finding something. Okay, so everywhere should be finite. And based on that, 3.5 say quadratically integratable. And this is directly derived from here. Which simply means when you do the normalization or when you do the evaluation of the probability, this part should be valid. If it's not finite, this cannot give you a finite number. It's simply means that. So based on all the four, or actually all the three requirements, you can tell me which function or functions A or R will be area functions. Again, we need to this one thing. The tricky description.
D.
Well, good at that stuff. Just D. Okay, what's the formula for A?
Not going to change.
It's not finite everywhere. Right? When x equals 0 it goes to infinity. It's not finite everywhere. What's the formula for B? More than one. Not single value. Okay, if you choose one x, actually give you 2 y. And even if you choose here A, it gives you infinite y. Okay, so it's not single value. How about C? What's the formula for C? No, you forgot in your math. This is a really typical example for showing a non-continuous function. Okay, and this function is not continuous at x equals 0. It's not continuous. So simply means at here, you cannot differentiate that function. Okay, there's no differential for that point. So here, true, right? This is what? Finding the box wave function actually contains this term. So it's a valid wave function. Alright, so that's so much for today.
Thank you.
See you.